recording everything here, we have the opportunity to just redo stuff. Okay, what we're going to look at here for the AP Physics 2 class is energy levels of an atom. We know that with Bohr's, planetary or orbital model of the atom, we have these idea of energy levels that exist. If we think about here is a positive nucleus, we can think about there is a perfect circle of an electron orbiting it in some way. We know this is not the case. We know that we have our proper spheres or electron clouds that things are going in, a sphere, and then the kind of like barbell system, and the kind of flower petal for your SPD orbitals. But let's just for right now pretend Bohr's right, because a lot of interesting stuff comes out of this idea of an orbital electron shell. What we're going to look at for these shells, though, instead of thinking of an orbitals with circles, it's a lot easier to think of them as kind of energy levels that exist, kind of building a stairway upwards. And it's important to note that as you go upwards in energy levels, you actually get smaller and smaller gaps in that energy level difference as well. So that's an important thing to keep in mind. What we're going to look at for our hypothetical atom is we're going to look at just some made-up creation of 4 energy levels, 0 electron volts, 1 electron volt, 3 electron volts, and 6 electron volts. These are going to be our 4 levels of the atom. And unlike chemistry, chemistry likes to start from 0 and then build upward, but it makes things weird whenever we start looking at equations. We are actually going to build our model upside down, so to speak. So whenever we create our energy levels here, what we're going to have is we are going to have 4 lines. The first line is actually going to be at -6 electron volts. And this is going to be n equals 1. The principal quantum number here is going to be 1 for that. This is our ground state. Okay. Our second level is going to be at -3 electron volts. This is n equals 2. This is actually what we can refer to as the first excited state. So that's a little annoying. We have the first state down here, n equals 1, but n equals 2 is the first excited state because we've bumped the electron up by some level. For our other levels we have here, we have 1 electron volt, and it's important that as we draw these lines, if we're drawing them in a way to scale, we're starting to close the distance between them. There's less of a spacing. And as we get to 0 electron volts, our last level, we have, oh, it's not moving for me. Look at that, that's annoying. Doing it by hand. We even have less of a spacing there. So computer doesn't want to do it, so I will force it to do it. Boom, there we go. Okay, so this is our hypothetical atom. It's been constructed like this. Now if we kind of zoom in on this, make this the center of our attention here. Whenever we have a hypothetical atom or just some atom in actual existence and we have our energy levels, we can draw kind of our transitions here. Now transitions for an atom can go 2 ways. They can go up or they can go down. Whenever you have a transition going upwards, what we normally have is that the electron has gained energy. And normally the way it gains this energy is through a photon of light. So normally it's hit by some sort of photon and gains that energy. You can go from the n equals 1, and if we label these are n equals 3 and then n equals 4 for our last one. You can go from n1 to n4, you can go from n1 to n3, you can go from n1 to n2. Technically you can do the things in between as well. You can jump up here, jump up here, jump up here. But these ones where I'm going from N2 to N3 and then N3 to N4. These ones are rare. Undo. Normally what happens as you're trying to do these is that you actually get a D citation. Your electron actually jumps down in levels. And if we think about this, if we're all the way at the top, we can come back down here. Going back down, the electron is losing energy, and when it does this, it emits a photon. So it emits light here. And if we're up at n equals 4, we can go all the way down to n equals 1. We could go to n equals 2, and then down to n equals 1. Note there's a photon here and a photon here that's released. Or we could go from n equals 4 to n equals 3, and n equals 3 to n equals 2, and then n equals 2 to n equals 1. And there's actually a photon that is released at each stage here. So something to be aware of for that. If we only were up at like the n equals 3 stage, we could go down from 3 to 1, or we could go 3 to 2 and 2 to 1. We've technically already done the 3 to 2 and 3 to 1 right here. So if you don't want to draw that again, you don't have to, but technically it could occur. And kind of the boring one is if we're at N2, we can go back down. And we've already drawn that one over here. So there's some overlap in what we've drawn here to some extent. Big key to remember is that going up is a gain in energy for our electron. We normally had to hit it with something, most often light. Coming down is a decrease in energy for our electron. And when we go down, we are emitting photons at each and every step of the way. Now, when we are emitting these photons, we often can say that the energy of the photon, we know that's equal to Planck's constant times the frequency. The way we normally do this is we take the energy of the upper level we're at minus the energy of the lower level we're at. And the reason we do this is if we normally think about this diagram, and this is just how physics thinks about it, which is kind of backwards from chem. When we think about going down, going from the N2 to N1 state, we are emitting an electron. So when we do upper minus lower here, what we have is -3 electron volts minus a negative, that's where we get this positive here, 6 electron volts. And when we do that, we end up getting a +3 electron volts out of that. And that is the energy of the photon emitted. And it's a positive value because it has this energy. If we built this the other way, we'd have to kind of redefine how we do some stuff, and it gets a little weird. It's just not how physics has done things traditionally. It's not saying that you can't. If you like how chemistry has their setup, have fun with it. This is just how we do ours here. Okay. So this is kind of the general idea of what we're thinking of. We're thinking about going up, or more importantly, coming down and emitting some photons. If we're going up or down, and let's just consider the down scenario every time here, we can look at this diagram and determine a few things. We can actually determine which photon released out of all of the red down arrows has the highest energy. To do that, we're just looking for the largest gap. So the highest energy, and let's not use yellow, the highest energy equals the largest gap. And if we look at this coming down, it looks initially like the largest gap might be from 2 to 1. But that's not a correct answer. Our largest gap is actually all the way up at n equals 4 down to n equals 1. So our largest gap size here is from 4 to 1. We can jump through the other energy levels, emitting that photon. So that's our highest energy. For our lowest energy then, that's the small gap, or the smallest gap. And our smallest gap is actually going to be located between our uppermost energy levels, 3 and 4, because we're only doing this tiny little bit right there. So between the 4 and 3 position, that is our smallest amount of energy. Now, normally whenever you have questions regarding these kind of diagrams or these setup, the energy isn't what you're going to be asked about, because the energy, you just see it from the diagram. What's often asked about is, hey, which one of these has the longest wavelength or the highest frequency? And normally they ask wavelength because that makes life a little harder. What we have to recognize if we're given a wavelength problem here is we can say that while energy equals HF, we know that C equals lambda F, where lambda is that frequency, or lambda is the wavelength that we're looking for. If we want to find or set up that lambda, it's equal to a constant divided by frequency. So if we're looking, and let's just say here that we're going to look for the longest wavelength that exists, well, that means we want this lambda value to be very, very high. If lambda is going to be very, very high, it's very, very large, that means the frequency needs to be very, very small. A large frequency is going to create a large denominator. It's going to bring down our lambda. So we want a small frequency here. Well, when we look at this, a small frequency is given by a small energy, because h is just Planck's constant. It's not changing. So to get a small frequency or a large wavelength, we need a low energy. And the lowest energy that's going to exist for us is, like we said before, 4 to 3. So we actually know that a low energy gives us a low frequency, which gives us a long wavelength. If you don't want to kind of work through this kind of logic, come exam day, what you can also think about is this. Looking at the electromagnetic spectrum, that red light on the visible wavelength has very long wavelengths with respect to the purple light. And if we go beyond red into the near infrared and then the far infrared, and then beyond that into microwave and radio, those wavelengths are wavelengths of a few meters. Like radio wavelengths are 1, 2, 3 meters in length. They are very low energy. You're not worried about them striking you. I mean, you've got radio waves going all the time. Like you get in your car and there's radio waves there. They're very low energy. They're not interacting with you. Also due to their wavelength. If you think about X-rays, ultraviolet rays, gamma rays, these are high energy wavelengths. We've talked about in class, if the Earth is hit by a huge gamma ray burst and is just irradiated with gamma rays, we're going to burn up the planet because there's a large amount of energy there. There's a lot of energy on very short wavelengths or high frequency. So if we think about it from that end, and just that there, if I have a high frequency, I'm being pushed into kind of my gamma ray, my X-ray end of things. Those are high energy, but my wavelengths are very short. If I want a large wavelength, I want low energy. And just by thinking about that, we don't have to think about the math anymore. We can just think about, hey, what's energy doing? Low energy is for your reds, your infrared, microwave, radio. High energy is for your violets, your X-rays, your UV light, your gamma rays. And then we can just think about that rather than working out the math. Okay? So that's some stuff that we have right there. If we wanted to see what kind of photon would be ejected from one of these transitions, let's pretend that we had an electron in the N4 orbital and then had it drop down to the N2. What wavelength would that have being kicked out? Now, if we wanted to do this, we just need to see these equations right here. Those are our bread and butter. Well, what we can actually do is, using this equation, we can format it a little bit differently to plug in what we're really looking for. We can substitute in frequency for C and lambda. We know that frequency is equal to C over lambda. So what we can do here is we can say that our energy is equal to H hc over lambda. And hc pops up often enough in modern physics that it actually has a value. It has a value of 1239, or most people just round it up to 1240 electron volt nanometers divided by lambda. Now, if we just have the energy here, we can put that in the equation and we kind of solve this out. And if we look at the energy, we're really looking at what is the energy difference between the N4, which is at 0 electron volts, and the N2 region, which is at 3 electron volts, so, or -3 rather. So what's the energy difference here? Well, if we do upper minus lower, or we just kind of think about counting, 0 minus -3 is +3. That's how we get our photon out. Or if we just go 0, -1, -2, -3, we have that value there. So what we can say here is that this is equal to 3 electron volts of energy. And if that's the case, this becomes pretty quick. We can bring the lambda up. We can bring the 3 electron volts underneath by dividing. And we can say that lambda, or the wavelength of this light, is going to be 1240 eV nanometers divided by 3 eV. Our EVs go away. We have nanometers, which is what we normally want light to be in anyways. And 1240 divided by 3 gives us something around 413, 414, whatever you really like there, nanometers. So that's not too bad, using primarily this EVs to nanometers. If you didn't want to use that 1240, what you'd have to remember is that, and you'd have to do like a train track here or something, a unit conversion, dimensional analysis. You have to remember that in 1.6 times 10 to the minus 19 joules, that's an electron volt, there is 1 electron volt. And then if you knew that you had 3 eV, you could convert that way into joules and then play around with that using Planck's constant. So that's one way to do it. I prefer this method right here. That's way, way faster, the 1240 eV nanometers. So that's some things we can just kind of do with a setup like this, looking at a hypothetical model of an atom. We're thinking about these energy levels that we exist in. The only last thing I have to say about these energy levels, and it's kind of a minor point, well, it's a major point that, you know, we kind of tuck to the side. Whenever these electrons are making these transitions, they have to make full level transitions at a time. You can't go halvesies. So if an electron is going to go from the N1 state upwards, it has to go all the way. There is no ability for this electron to go halfway from one photon of light and then go, okay, I'm going to wait out here, and then wait for a second thing and then do that. That is not allowed. You can't do that. It has to be one transition at a time. On the same flip side of things, you can't, you know, go down here for like a little bit of light and then the whole way to get two independent things. We know this to be true not only from experimental data that we kind of see, but if we think about what Max Planck did, saying that the energy of light is quantized. Well, it's quantized through these energy levels, such that if we looked at an emission spectra of some light, whether it be hydrogen or helium, we don't see a continuous band. We only see specific points of light that exist at specified wavelengths. And those specified wavelengths are what we get through these various transitions here. Okay, so we know we're going to get certain wavelengths of light out based on the certain hypothetical atom that we have. Okay, so that's an important thing to keep in mind for that. With that though, that's kind of basically the big structure of looking at an energy level diagram, what we can do there. Keep in mind, highest energies are for the largest gap, lowest energies are the smallest gap. And in terms of, hey, what has a long wavelength, what has a short? Well, I know low energies are kind of my red infrared light. I know high energies are my ultraviolet light. Red light's got a very short frequency, a very long wavelength, and just the vice versa for the very high energy light, very, very short frequency, or a very, very large frequency because they're very short wavelengths. They're all tucked together there. So something to keep in mind for that. With that, though, we're finished with that. That's kind of the rundown there.